Motors are the most common application of using magnetic force caused by current-carrying wires. Basically, if you have a wire loop inside a magnetic field, the force acting on each part of the wire creates a torque that powers the motor. We know that an electric current moving through a magnetic field will feel a magnetic force because of that magnetic field. Here we have a uniform magnetic field, and inside this field is a loop of wire that has a current moving in a clockwise direction as indicated by the blue arrows. The magnetic field is uniform, but at different points along the wire, the current is flowing in different directions with respect to the magnetic field. We can start off in this first section at the bottom of the loop. The current will be going to the left at an angle parallel to the magnetic field. Parallel lines do not have an angle separating them, so the sign of 0 is 0, giving us zero force caused by the magnetic field. This will be true for all parts of the wire that are parallel to the magnetic field. Looking to the left side of the loop, we see that the current is moving in a direction perpendicular to the magnetic field. We can use our right-hand rule by lining up our fingers with the current and curling them so that they follow the magnetic field. This gives us a force that would be moving into the page. On the other side, the current is moving in the opposite direction, so it would make sense then that the force would be moving in the opposite direction, or out of the page. So over on the left, we have a force pushing the wire inward, and on the right, we have a force pushing the wire outward. There are no other forces acting on the wire, so the question now is whether or not there is a net force. If our magnetic field is uniform, the force pushing down should be equal to the force pushing up, so there is no net force. But there is something happening. That coil of wire is going to be moving. So while there is no net force on the wire, there is a net torque that will allow the loop to rotate around some axis. We can, of course, calculate the net force acting on our wire. Torque is essentially work in a circle, so we need to take the force times the distance. In this case, we are talking about the force created by the magnetic field, which we know to be ILB and the sine of theta. Since the force is acting perpendicular, we can ignore the sine theta at this point. But as the loop rotates within the magnetic field, the angle changes, and we will need to account for that. L will be the height of the wire that is perpendicular to the magnetic field. D in the torque equation refers to the distance from the axis of rotation. The width of the wire loop is designated W. And if we are only talking about the torque on one side, we would divide the distance by 2. However, in this situation, we really cannot separate out the two forces from the total torque, so we can leave the distance written as the length of the wire loop. So the torque created in a magnetic field is equal to the strength of the current times the length of the wire within the magnetic field times the strength of the magnetic field times the width of the wire loop. Even better, we can see that there's a length and a width in that equation, which we can write as an area. This is especially helpful when we don't have a nice perfect square to work with. Now one last thing, this equation is written with the idea that there is a single loop in the wire. Adding more wire would cause more current, which would then cause more torque. So we do need to account for more than one wire. This is done by adding in n as a representative for the number of loops in our wire. Alright, the torque that a current-carrying loop feels in a magnetic field is the number of loops times the current times the area times the magnetic field and the sine of the angle between the current and the magnetic field. There are a lot of situations where you might want to separate the geometric component of this particular equation from the part of the equation describing the magnetic field. When we say the geometric component, we are really talking about the wire itself, so this would include the number of loops, the current traveling through the loops, and the size of the loops. This is what we call the magnetic moment. Torque on anything is the magnetic moment times the magnetic field. We can also look at this from a bird's eye view and see a bit more of what is happening with the forces. We started our loop in an orientation that was straight up and down with respect to the magnetic field. This diagram has a lot going on, but the black line represents the top wire of our loop with the current moving up from the left side to the right side and then down into the page. The force on the left side is perpendicular to the magnetic field, and remember in our description we said it was going into the page, so from this view it is acting in the up direction. On the right side, we said the force was coming out of the page, so in this view it is going in the down direction. also perpendicular to the magnetic field. This orientation makes it pretty easy to see that the wire will rotate in the clockwise direction. The loop will rotate a quarter turn so it is now perpendicular to the magnetic field. If we look at the bottom of the loop, the current is going into the page, and if the magnetic field is to the right, the force will be acting in a direction straight out from the loop. Same thing at the top. The current is coming out from the page, indicating a force moving straight out from the loop. At this point, there is no torque acting on the loop. Inertia is what is going to keep it rotating. But as it moves past the point with no torque, the wire with the current moving out from the page enters the opposite side of the magnetic field. This reverses the forces on the ends of the loop, and the loop rotates back the other way. So inside this magnetic field, the loop would simply oscillate back and forth. Since we typically want the loop to keep on rotating, what we do is just at the right moment, we reverse the current. So instead of the force acting to turn the loop back, it acts to push it on through. Then when the loop gets over to the other side, the current reverses again, pushing the loop through the magnetic field. Suppose a circular loop of wire has a diameter of 20 centimeters and contains 10 loops. The current in each loop is 3 amps, and the coil is placed in a 2 Tesla magnetic field. Determine the maximum and minimum torque exerted on the coil by the field. Well, we're looking for torque, and the only thing we don't know here is the area of our wire coil. Our torque equation is valid for any shape of coil, so we just need to figure the area. Maximum and minimum torque depends on the angle the coil makes with the magnetic field. The maximum torque is going to be when the coil's face is parallel to the magnetic field, which would make the angle 90 degrees. So calculating that out, we find the maximum torque to be 1.88 Newton meters. The minimum torque will occur when the angle is 0. Since the sine of 0 is 0, then the torque exerted at that angle is also 0. So a force or torque exerted on a current-carrying wire by a magnetic field depends on the area of the loop of wire, along with the number of loops of wire, and the angle the wire aligns with a certain magnitude of the magnetic field.